In this video, we're going to look at surjections and injections. So again, we have a linear transformation T from V to W, where V and W are vector spaces with scalars from the same field F. Now, V is called the domain of T, and W is called the codomain of T. Now, the range of T, denoted by range, open bracket T, close bracket, is the set of all possible outputs. So it's the set Tx such that x is a vector in V. Sometimes one calls this the image of T. Now, if you look at the range of a linear transformation T given by T of x equal to Ax for some matrix A, then the range is actually just the column space of A. We say that T is surjective or onto if the range of T is equal to the codomain, which is W. And such a linear transformation T is called a surjection. And we say T is injective or one-to-one if for all distinct xy in V, we have T of x not equal to T of y. And in casual terms, it means that different inputs lead to different outputs. And if T is injective, it is called an injection. So let's consider the linear transformation given by T of x1, x2 is x1 minus x2 and minus x1 plus x2. We're going to find out if T is a surjection or if T is an injection. Notice that every element in the range is of the form A minus A. And it's not hard to see that because this here, minus x1 plus x2, is precisely the negative of x1 minus x2. And so we can't possibly get everything in R2, right? Because, for example, 1, 0 is not in the range of T. So T is not surjective. What about injection? Well, if you look at T of 0, 0, obviously it gets mapped to 0, 0. But T of 1, 1 also gets mapped to 0, 0. So you have two distinct inputs that get mapped to the same output, and so T is not an injection either. If a linear transformation T is both injective and surjective, T is said to be bijective. Now, there are some criteria for testing surjectivity and injectivity. So, for example, if W is finite dimensional, then T is surjective if and only if the dimension of the range of T is equal to the dimension of the codomain. Because the range is a subspace of the codomain, and if they have the same dimension, then they must be the same vector space. And for example, say T is given by A times X for some matrix A, then T is surjective if only if the dimension of the column space is equal to the dimension of the codomain, because the range of T of X in this case is just the column space of A. But the dimension of column space is given by the rank of A. So T is surjective if only if the rank of A is the same as the dimension of the codomain. Now, to test injectivity, we just make use of the following fact. T is injective if and only if the kernel of T has dimension 0. Or another way to say this is the kernel of T has only the 0 vector. And in the case when T of X is given by A times X for some matrix A, then T is injective if and only if the nullity of A is 0. Or in other words, if you look at the system Ax equals 0, it only has the 0 tuple as the solution. Now, one important result that relates the range and kernel of a linear transformation is the following theorem. And it generalizes the Rank-nullity theorem for matrices. So if you look at the dimension of the range of T plus the dimension of the kernel of T is going to be equal to the dimension of the domain V.